This is problem 13. Imagine standing on the surface of each of the 6 astronomical objects listed below. Ignore the effects of all other nearby objects and the excitement of visiting these different places. So remember, with the Schwarzschild metric, we can only use it for one large mass because we have to assume the mass is at the origin. And we have to ignore the excitement because you're looking at the time between your heartbeats, and if you were really excited, your heart be beating fast. So, in part A, we're ranking these situations on the basis of the time between your heartbeats as measured by you. Although faraway observers would look at you and see that in the presence of a gravitational field, time would be going slower for you yourself, everything seems normal when you measure your heartbeat. And so, because this is measured by you, all 6 should be equal to each other. So A is equal to B, is equal to C, is equal to D, is equal to E, is equal to F. If you think about back in special relativity, if you were traveling fast on a spaceship, you'd still, if you're using a clock in your own reference frame, so if you are using your Ross watch to measure your heartbeat should be normal. So, in part B, now we're going to rank these situations on the basis of the time between your heartbeats as measured by someone very far away. So, ignoring the excitement of being on the surface of a large astronomical object, the time between your heartbeats should be the same for you. So, if we look at ds squared first, using what you measure, that would be using the Minkowski metric. And we're looking at the time interval, so this would be for you. And you're not moving anywhere, so dx is equal to 0. So for ds squared, we just have c dt sub y squared. Then we compare that to what a faraway observer would measure, and the faraway observer must use the Schwarzschild metric because the faraway observer can tell that where you are, space-time is warped and time is going slower for you. Well, they would look at you and say time is going slower for you because you're in the presence of a large, massive object. But again, dr squared and d phi squared are equal to 0, so we would just have 1 minus 2gm divided by c squared r, and measured by someone very far away, so let's call this c dtf squared. Now, we're going to look at this and take the square root of both sides. And let's cancel out the c also. Whoops, no, it's not equal to that anymore. So we have dty is equal to the square root of 1 minus 2gm over c squared r times c dtf. But what we know is what you measure, and what we're trying to find out is what a faraway observer would measure. So dividing both sides by the square root of 1 minus 2gm over c squared r gives us this equation, which we are going to use for our ranking. Also remember that the 2gm over c squared is the event horizon, so you could calculate the event horizon first and then just say this is the square root of 1 minus the event horizon divided by r. Now, because it's a ranking problem, we can say dty is the same in all 6 situations, and 2 is a constant, capital G is a constant, c squared is a constant, so we can rank on 1 divided by the square root of 1 minus the mass divided by r. That's the mass that they give us here. This is the solar diameter. Why do they do that to us? Because we want the radius and not the diameter. However, if we use the diameter, it's not actually going to change the ranking, because to get the radius we would divide each of these by 2, but since it's a ranking problem, that would have the same effect in each of the 6 situations. Now, I want to do less math than what I have here. So if I can just think about how this ratio will change my ranking, when m divided by r is greater, and do we have a problem here because we're subtracting this from 1? So it looks like if m divided by r was too great, then 1 minus that would be negative, and then we'd get something imaginary. But remember that this came from our equation here, and I said that you could do our event horizon divided by r. So this would be less than 1 when r is less than the event horizon. But you can't do that because if r is less than the event horizon, you have lost all contact with the rest of the universe. Okay? So, if we were talking about a black hole, if r was less than the event horizon, you'd be inside the black hole, not in contact with the rest of the universe. So, we shouldn't have to worry about that for any of the objects here. We still have an event horizon, but the event horizon should be inside the object, so that should be less than what we have for the radius for the surface of the object. So we shouldn't have to worry about that. You can always calculate the event horizon just to make sure it is less than the diameter of the object. So now that we've got that taken care of, when we do our ranking here, this should be less than 1, and like what I did here wasn't completely correct, but it will be fine, because we're just going to say, based on this, when m divided by r is larger, it's still less than 1, so it'll be 1 minus something like 0.9, which would give us 0.1. Then we take 1 over the square root of that. That's in the denominator. So when m divided by r is larger, we have something smaller in the denominator, which is going to give us something larger overall. So I'm just going to put it up here. When m divided by r is larger, DTF is larger. So that is how we are going to do our ranking. So then up here in my table, I'm just going to add another column. And this is going to be for the mass divided by the diameter, which again isn't exactly what we have in our equation here, but since it's a ranking problem, it will all work out. Okay, so for the sun, the mass is the solar mass, and the diameter is the solar diameter. So for the sun, we just get 1. Okay, and then here for the Earth, we have 0.000003 and 0.009. So this is 3 times 10 to the negative 6th. This is 9 times 10 to the negative 3rd. So 3 times 10 to the negative 6th divided by 9 times 10 to the negative 3rd is equal to 1 over 300, which is 0.003 repeating. Okay, now for our red giant, that would be 18 divided by 78. However, because it's a ranking problem, I think I can get away with just saying this is approximately equal to 20 divided by 100, which is equal to 0.2. So this is approximately equal to 0.2. Can do something similar for the blue giant here. Rather than doing 17 divided by 936, I can just say that's roughly equal to 200 divided by 1,000, which is 0.02. And as long as the numbers that we get here aren't really close to each other, we're fine with doing approximations here. So this is approximately equal to 0.02. And then for E, this is 1.4 divided by 0.00000014. So that's 1.4 divided by 1.4 times 10 to the negative 6. So this is 10 to the positive 6. And then for our last 1.6 divided by 0.012 is equal to 50. So this is 10 to the 6th. That is far greater than anything else in our table. So the largest one will be E. And then after that is F. And then I have A. And then C. And then D, and then B, and B is an order of magnitude smaller than D, so I should not have to worry about the fact that I did round. Okay, now actually, I just looked at my solution, and I see I was incorrect when I told you that you don't have to worry about this being greater than 1. It actually is greater than 1 for the neutron star. So let's calculate the event horizon for the neutron star. That would be our event horizon is equal to 2 times G times M, which is 1.4. And remember, this is a multiple of the solar mass, so that would be 1.4 times 1.993 times 10 to the 30th. And then divide by c squared, so that's 2.998 times 10 to the 8th. Let's just leave the units off. That is 4144 meters. And then for R, that would be 0.000014, so that's 1.4 times 10 to the negative 6, but that's a multiple of the solar diameter. Oh, but wait a minute, here we actually do have to divide by 2 because this is the diameter. Oh wait, we don't even have to worry about that because when you look it up in the table, it's the radius, so that's fine. Instead of multiplying by the solar diameter, we will multiply by the solar radius. So this is 6.963 times 10 to the 8th, and that gives me 974.8 meters. Since R is less than the event horizon, you are inside the event horizon and you have lost contact with the rest of the world. So maybe we should put E down here. I'd be fine if it was a homework problem and you left it there though, because before you get to this R here, which is inside the event horizon, the rest of the world would see you at the event horizon and it would be like time was standing still for you. So your heartbeat would, the time between your heartbeats would go to infinity before you even got to this distance. So if you wanted to leave it there, that'd be cool.